Hi everybody and welcome to Six Sigma and Processi Produttivi YouTube video channel. This is my third video in English about this topic, which is the process capability and relevant indexes CPK and PPK. We can now have a look at the introduction slide that you can see here. It's named CPK and PPK Process Capability Part 3. Because, as already said, this video is the last one of a series of 3 about the process capability. Let's start with a short recap from my previous tutorial. So let's start with CPK and PPK formulas. CPK is the lower value between CPL and CPU. You can see here the CPL formula, where at the numerator, we have the average represented by X bar, average of the values obtained by measuring few units sampled from drawn from a first sample from my process, minus the lower specification limit divided by 3 times the standard deviation of the values obtained by measuring the units drawn from my sample. CPU, we have the formula here, upper specification limit minus the average, X bar, divided 3 times the standard deviation. The same definitions of average and standard deviation apply as we explained for CPL. PPK is the lower value between PPL and PPU, and if you remember from my previous tutorial, PPU equals CPU, PPL equals CPL. The difference is in the standard deviation at the denominator, which has a different meaning. The standard deviation for CPL and CPU is called standard deviation within, while the standard deviation for PPU and PPL is named standard deviation overall. The higher is the CPK and more the Gaussian curve representing my distribution of data will be centered and narrow with respect to the upper specification and lower specification limits. Here we have a very easy and clear graphical representation. You can see here the 2 vertical bars representing the upper specification limit and the lower specification limit. In this case, which is an ideal situation, the Gaussian curve representing my data is well centered with respect to 2 limits and very narrow. So all of the values are very far from the upper specification limit and the lower specification limit. The same applies for PPK. And now we are ready to make an example of our CPK and PPK calculation. Let's go back to the example shown in my previous tutorials of the data distribution obtained by counting the number of M&Ms in each of the 20 bags taken from production day number 1. If you remember, in my previous tutorial, we were talking about MMM's Corporation, production day number 1, a new primary packaging machine designed to pack bags of MMMs with 2 specification limits. The data are represented here, the same data shown in previous tutorials. So we had the 6 bags containing 28 M&Ms, 5 bags containing 27 M&Ms, 4 bags containing 29 M&Ms, and so on. And the specification limits were upper specification limit 31 and lower specification limit 25. This means that MMM's Corporation will consider so passing the specifications, a bag containing a number of M&Ms included between 25 and 31, where 25 is still okay and 31 is still okay, while if the number of M&Ms in a bag is outside these 2 limits, so for example 24 or 32, it's outside of the specification limits. Before to calculate CPK and PPK for this specific example, let's take into account that we have some conditions to apply. The first condition is that we are talking about just one sample drawn from my process, in this case, one sample drawn from production day number 1, and just few units, in this case 20, from my single sample drawn from my process. In this case, Cpk can be considered equal to Ppk, because equal can be considered the standard deviation at the denominator. If you remember from my previous tutorial, this is the formula of the standard deviation used for Cpk and Ppk calculation. This is the standard deviation overall. If these two conditions apply, the standard deviation within can be considered equal to the standard deviation overall. Let's recap also that the standard deviation overall is used to calculate Ppk, while the standard deviation within is used to calculate Cpk. Now we can proceed with the calculation. These are the data, so 6 times 28, 5 times 27, 4 times 29, and so on. And on the above listed data, we have to calculate the average, represented by x bar, and the standard deviation, represented by sigma. You can do this with your mobile phone, with your PC, with Excel. The average turns out to be 27.8, while the standard deviation turns out to be 1.32. Of course, we have decimals. Decimals are not so meaningful in this case, because we are talking about integer data, because the number of M&Ms in a bag can be only an integer number, but due to calculations we have decimals. So PPL, which is almost equal to CPL, if we apply the formula, will be these numbers. Okay, so instead of the average, we place 27.8, which is exactly the average we have obtained. 25 stands for the lower specification limit, 3 times the standard deviation obtained on my 20 data, which is 1.32, and we get a value of PPL of 0.71. We can make the same calculation for PPU, the same process apply. The only difference is that instead of USL, we put the value 31, and we get a PPU value of 0.81. So at the end, which is the lower value between the two is 0.71. So PPL is 0.71, and in this case, 0.71 is also the Ppk, and we can say that the Cpk is more or less the same value. But having obtained a Ppk value of 0.71, are we satisfied of this output? 0.71 can be considered a good output? Well, when dealing with just few units taken from just one sample from a production process, these are the two conditions that apply, that I showed in the previous slide. The industry standard practice in these conditions establishes a minimum value, and the minimum value is that Cpk or the Ppk should be equal or higher than 1.33. Well, you immediately conclude that our process, that is, in this case, an M&M's primary packaging machine, is not performing as it should, because the Ppk obtained is not 1.33, but it's 0.71. Well, a typical approach in the industrial process would be the following. Start the process, for example, introducing in the production area a new primary packaging machine, production area at M&M's Corporation, just producing few M&M's bags, count the number of M&M's in each bag. That's exactly what we did, but simply ensure that each value is just within specification limits that are 31 and 25. Well, our 20 data were exactly within specification limits. All of them were between 31 and 25. And the typical approach, which we will see later on that is wrong, is to just ensure that the values obtained, just these few data, are within specifications, and then start a mass production to discover only at a later stage that the average production scrap rate is too high and economically not sustainable. And this approach is wrong. Why? Because we have seen that it's not enough just to see, just to verify, just to ensure that each of the 20 values is within the specification limits. But we need to calculate the process capability. The right approach would be to launch a pilot run from which to draw a first sample of 20 units, and then on said sample to perform a process capability analysis and see if the outcome is what should be expected, so a value equal or higher than 1.33. Proceeding this way, it would be easy to immediately discover in advance, proceeding this way, which is the right approach, that the CPK value obtained would be insufficient, so it would be possible to predict before entering mass production that the new primary packaging machine, in our case, will generate on future mass productions an average scrap rate of 2.5%. So instead of producing only few bags, just ensuring that each value is within specification and then go into mass production, take these few samples, calculate the process capability, and see if the process capability, this is the right approach, is at least equal or higher than 1.33. Only if you obtain an outcome like this, then you can go to mass production. Because if you do in the wrong approach, you would have an average scrape rate of 2.5%. How do I know that? This could be the question that many of you are thinking in this moment. We will see this in a few minutes in Minitab. So the right approach would be, after having obtained a ppk value of 0.71, would be stop for a while, have a look at the new primary packaging machine parameters and settings before entering mass production. Then try to adjust this parameter and setting, run again a pilot run, take few samples again from this pilot run and recalculate the CPK and PPK indexes. And we should expect that the new PPK and CPK value are higher than the previous one, probably at the target of 1.33. And at that point, we can enter mass production. Because if we don't do this way, okay, we will have scraps, and so we will lose money, okay? Because at the end, the process capability analysis is a statistical tool that gives us the possibility to save time and money, because at the end, process capability equals Six Sigma, we already know this, and equals scraps reduction. Just looking at few samples and just verify that they are within specifications will lead us in a wrong approach, thus leading to a lot of scraps. But we now jump in Minitab, and we will see in Minitab how to replicate the same calculation just obtained here in this PowerPoint presentation and how to obtain the 2.5% scrap. Hi. Welcome to Minitab. This is the initial worksheet when just clicking on Minitab icon. I have summarized some data for you. The data obtained in the PowerPoint presentation, where we obtain a PPK of 0.71, a CPK that is more or less roughly equal to PPK. PPU was 0.81, PPL was 0.71. The average of the 20 values obtained by measuring the 20 units sampled from the process was 2.78, and the standard deviation was 1.32. Well, before going to the PPK and CPK calculation in Minitab, I want just to stop a little bit on the 2% percentage scrap rate that we have introduced in the PowerPoint presentation. Probably some of you would think that it's not a big deal, it's not a big problem, 2.5% scrap rate, because it seems a low value. But if we think that primary packaging machine that we have figured out can produce most likely one piece every 6 seconds, and we have 3,600 seconds in an hour, this machine would be able to produce 600 units in an hour per, let's say, 2 shifts, because at MMM's Corporation, this kind of machine would be able to produce for 2 shifts that are 16 hours. Let's consider 15 hours because maybe 1 hour can be dedicated to operators breaks or maintenance breaks. Okay, let's figure out 15 hours. 15 hours per 600 would be 9,000 units per day. For 220 working days per year, more or less, it's about 2 million pieces per year. This is the process capacity of a machine like this. If we consider 2.5% of 2 millions of pieces, it would lead to 50,000 scraps per year. Okay, 50,000 MMMs bags scraps per year is really a huge number. That's why 2.5% scrap rate is a huge number. But let's see how to obtain this number. So let's go to make the process capability calculation in Minitab. You can see here the column with the 20 data are the same data that we have seen in the PowerPoint presentation. Just 20 data, as you can see here, 6 times 28, 5 times 27, 4 times 29, and so on. Okay, let's go then to stat, quality tools, capability analysis, normal. Why normal? Normal because we have already seen in previous tutorials that exactly these 20 data follow the normal distribution. We already performed the normality analysis and we obtained a p-value more higher than 0.05, so we can perform the process capability analysis with the normal option. Here where it appears this window in the field, the single column, we click on the only column that features the data, so C1. Subgroup size is a topic that we haven't explained so far, but you remember the 2 assumptions, just a few data taken from one single sample taken from a process. In this case, Cpk is almost equal to Ppk. That means that the subgroup size equal to the total number of samples drawn. So in this case, the subgroup size would be 20. The lower specification limit, if you remember, is 25. The upper specification limit is 31. So just clicking OK, we will obtain this beautiful graph here, where we immediately see here a ppk of 0.71, which is exactly the value that was expected basing on the calculations handmade in the PowerPoint presentation. We can see that ppk 0.71 is the lower value between ppel, that is 0.71, as we can see here, and ppu 0.81, as you can see here. Okay. And we see, for the same reasons, that Cpk, Cpl, and Cpu are most likely the same values obtained for Ppk, Ppu, and Ppl. In fact, they are 0.70 and 0.80. 0.70 is almost 0.71, and 0.80 is almost 0.81. Here on this label on the left, we have the lower specification limit that we entered, 25, the upper specification limit that we entered, 31, and it has been obtained 27.8 as an average, as you can see here, and exactly the standard deviation overall, which is the one used to calculate PPK, which is exactly 1.32, as you can see here, while the standard deviation within is similar, not exactly the same. That's the reason why CPK and PPK are not exactly equal, but there is a slight difference. Okay? Well, now we have only to see where 2.5% scrap rate comes from. Well, if we discover this second part of the graph, we see a level here in at the bottom of this graph, and we can see here an observed performance, an expected overall performance, and an expected within performance. Let's stop a few seconds on the observed performance. You can see always 0 here. Why? Because we have 20 values, and all of the 20 values are within specification. There is no value outside, so higher than 31 and lower than 25. So the observed performance is that there is no value outside of specification, so we have 0. But the expected overall performance is what we are interested in. So what will happen in the future? What will happen on huge numbers? What will happen when jumping in mass production? Well, we can see here 17,000 ppm. ppm means part per million. 17,000 ppm means that in my future production, if I will produce for 1 year, 2 years with this new primary packaging machine, I will obtain 17,000 bags per million outside of the lower specification limit, means values below 25, so outside by this side, okay, of the graph. 7,743 units outside of the upper specification limit, so more or less 8,000 bags per million above the upper specification limit. So the upper specification limit is here, so we have the values that will be outside from this side, so higher than the upper specification limit. In total, I will have 24,822 bags per million outside of both the specification limit, but 24,822 bags per million means exactly 2.48% scrap rate, which as approximation is 2.5% scrap rate in futures production. So you will see here how to get this 2.5% scrap rate. And this is a tremendous powerful tool, because just with few units, 20 units taken from a first sample from the first day of production at MMM's Corporation, we are able to immediately understand what will be the percentage scrap off rate, and then we can make all of our considerations, all of calculations about the money, the number of scraps we will produce on future massive production. And if we don't use the process capability tool, if we don't use this powerful tool, and we just rely on the fact that the 20 units are all of them within specification, and this is given by the observed performance, which is 0, we will make a big mistake, because we will jump to massive production without taking care all of the scraps that I will produce in the future. Well, dear all, this tutorial is finished. I hope you have enjoyed it. Please put a like in YouTube if you have enjoyed it, and don't forget to subscribe to the channel. This is the last video about the process capability, but there will be new topics upcoming in English. Thank you everybody for having stayed with me, and I wait you at the next tutorial. Bye bye.